Hi, welcome to 21st session on group theory. Today we will focus upon normal subgroups. Normal subgroups are very important in the structure of groups. Okay, and we had already seen a class of normal subgroups which arise as the kernel of homomorphisms. Okay, if F is from G to H is a group homomorphism, and if K is the kernel, then we found K has some two important properties, namely for every element A in G, A K, the left coset, is equal to H Ka, the right coset. And more importantly, for every X in K and for every A in G, the conjugation of X by A, that is AX, A inverse also belong to K. Okay, and not all subgroups have this property. We will look at some example also. So our focus will be, we will define the subgroups to be normal subgroups which if it has these two properties, they are actually equivalent. Okay, that's going to be the focus of today's lecture. Let us get started. So let us assume G is a group. Okay, H is a subgroup of G. We say that H is normal, is a normal subgroup of G if, okay, for all A in G and X in H, the conjugate AX, A inverse, AX, not okay. This belong to H. Okay, sometimes we will simply say H is normal in G. A subgroup is normal in G. And the standard notation in group algebra books is this. H is normal in G. Let me write it. So H is subgroup, we write like this, you just put it here, then it's normal. That's it. Okay, right. Let us just quickly look at, not all subgroups are normal by looking at, okay, let's look at first examples. Examples 1, this identity group and G, they are normal subgroup. This is very trivial, right? Okay. The second thing, if F is a group homomorphism from G to H, then K, which is the kernel of F, that is defined to be set of X in G, so that Fx equal to identity, this identity element of H. I will not write it. Okay, then K is normal subgroup. That is K is normal subgroup of G. Why? Let us look at X in K and A in G. Let us, you want to know whether AX, A inverse belong to K. So when does this belong to K? That belongs to K if only if the only defining condition is F for that element should be identity. That is F A X A inverse should be identity. This is what you want to know. Right? But this, since F is a group homomorphism, this is same as F of A, F of X, and F of A inverse, but is F of A inverse. Right? But what do I know about F of X? It's identity. And this is identity. Therefore, I get identity. This is identity of element of H. Remember that. Okay. So K is normal. Okay. Pause. Review. Proceed. The third example, suppose H is a subgroup of G, but the index of H in G, that is what, remember, that's the number of cosets. If you want left cosets, you can also do with the right cosets of H in G. We usually denote by G is to H with the bar. Okay. Suppose that is equal to 2, then we claim H is normal in G. Let me write the notation. Right? Okay. How do I prove that? So start with an arbitrary element X in H and arbitrary element A in G. Right? Then I have to show AX, A inverse, whether it belongs to H. Okay. Let me write. Let me be careful that I am using this, whether it belongs to H. Right? Now let's look at. I have to make use of the fact H, index of H is there. Therefore, if A is in G, okay, what is, then there is nothing to prove. Sorry, A is in H, nothing to prove. Because A is in H, X is in H, A inverse is in H, therefore product of elements must be in H. So AX, A inverse belong to H. Right? Suppose A is not in H. Right? If A is not in H, then G is actually H union AH, a disjoint union. Is it clear? Right. So if AX, A inverse, I want to say it belongs to H. Is this clear? Yeah. Now this is what I want to claim. Suppose it's not here, then where will it be? This implies AX, A inverse must be in AH, because this is a disjoint union. If it's not here, it has to be here. Right? That means what? That means AX, A inverse must be some A times some H1. Right? It belongs to any element of here in AH is of the form A times some element of H. So call it H1. Right? Now let us look at this. This is A, therefore multiplying both sides by A inverse, that gives me A into A inverse, that is X A inverse equal to A inverse H. Is that all right? Okay. Right. Now sorry, A inverse AH, that is, sorry, H, right? A inverse AH, that H1, that gives me H1 or H. It's just element. Okay. AH, A inverse must be some element here, call it A times H, multiplying by A inverse both sides. This will become A inverse into A will be H. The right side is H. Therefore X, A inverse is in H. Right? Now multiply on the right by A, that means X, A inverse A equal to HA. This is identity. Right? Therefore, again multiply by H inverse on the left, therefore H inverse X will be A. Right? Now what do I know about X? X is in H. H is in H, therefore H inverse in H. Therefore this element is in H. That means A is in H. That's a contradiction. Because if A is in H, then AH will be equal to H. Right? That means AH equal to H. But that's not true. Okay? So therefore, for all A in G, X in H, AX, A inverse is in H. Okay? Pause, review, proceed. Some of you who has already seen group theory, most often normal subgroup is defined to be if the left cosets are equal to the right cosets by the same element. Okay, and then therefore you will immediately conclude any subgroup of index 2 is normal, right? But I chose this approach. I will explain why I chose this approach. Okay, that is why once you know the subject very well full of mathematics, not only algebra in general, then you see which concepts are more important. Okay, they are the real spirit of the course. Otherwise, you just go by a textbook, keep on writing your proof. Don't get bothered, forget it. It's just some kind of academic politics. Okay, right? Now the third example is, let us look at G as a group. Okay, let us look at the set S, which consists of all elements of the form A, B, A inverse, B inverse, as A and B varies over G. You understand this? Product of four elements, you take any two elements. That, for example, identity has to be there because I take A equal to B, then it will be identity. Okay, this need not be a subgroup. But G is a group which contains S. Therefore, by our earlier analysis, there exists the smallest subgroup G dash of G such that S is contained in G dash. Okay. Recall how I defined the smallest subgroup, intersection of all subgroups which contain S. Okay. This is the smallest subgroup. Okay. Just take a minute, understand this. This is going to be, if which is a subgroups, class of subgroups containing S, then my G dash is intersection of H as H varies over script H. Okay. Now I claim my G dash is normal in G. Right? So what do I have to do? Start with an element A in G, X in G dash. Right? Then what I have to do? I have to prove AX A inverse. This belongs to G dash. Right? Now what is, I do not know how does G dash look like. I could have done it, but I didn't do it. But what all I know is you should contain any element of this form. A, B, A inverse. That is, take two elements, take their products in this way. A, B, A inverse, B inverse. That must be there. So somehow I have to make use of that. Now, AX, A inverse there, what is missing? Therefore, missing is A, X inverse, right? Therefore, A, X, A inverse and X inverse, that belong to G dash. Because A and X are in G, therefore this must be in G dash. Right? Okay. But where is X? X is in G dash. Right? So this element is G dash and X is in G dash. So therefore, let me take this element A, X, A inverse, X inverse. This is an element in G dash and then multiply by X, that is also in G dash, and G dash is a subgroup, therefore this has to be in G dash. But this element is what? This is A, X, A inverse, because these two get cancelled. Right? Therefore, G dash is normal in G. This G dash is called the commutator subgroup. And these elements A, B, A inverse, B inverse, because of various reason, one usually calls it this bracket operation AB. Okay. So AB, this is a notation. Sometimes some textbooks use. This has a meaning in other parts of mathematics. That's why this came about. But it's all right. Okay. Pause. Review. Proceed. Okay. So we are given enough examples. Okay. For example, if I take the alternating group AN as a subgroup of Sn, is it normal? Now we know for two, because of two reasons. Because if I look at the map F from Sn to plus or minus identity, which is F of any sigma, is sine of sigma, that we have seen is a group homomorphism. Its kernel is precisely the alternating group, right? Yeah, therefore alternating group is normal. The other thing is, what is the index of alternating group in Sn? We know, okay, number of elements in An is n factorial by 2. That is number of elements in Sn by 2. That means the index of An in Sn is 2. Therefore, it's normal. Therefore, there are two ways of looking at it. Is it clear? I didn't want to write. I deliberately chose to give the thing orally. I'm going to just write the result. Okay. I'm not going to write the proof. This is the fourth example or fourth. Okay. Fourth example. Okay. An is normal Sn. And the fifth example is, let us look at SLNR, SLNR, which is a subgroup of GLNR. Okay, these are all invertible matrices. That means determinant is not equal to 0. Here determinant equal to 1. Okay, this is normal. Why? That's very easy. Suppose I start with any x here and a here, ax, a inverse I want to say is in SLNR. The only way I know is I have to find the determinant, but determinant is going to be 1. X A inverse by various properties, this is going to be determinant of A, determinant of X, determinant of A inverse, that is determinant of A into determinant of X into determinant of A, this inverse. This is the 1 upon determinant of A is a number, therefore they get cancelled, I get determinant of X, but determinant of X is 1, therefore this is normal. Okay. Now I want to give an exercise. Let us look at our Ax plus B group. I hope you remember, right? There are two groups in that, namely that is f of any element is of the form AFB, or it is A10 B. Okay, so there are two obvious things. Not is f of A comma 0 as A varies over non-zero reals, or f of 0 comma B, sorry 1 comma B as P varies over R. Okay, check whether they are subgroups and check whether they are normal. Okay, this exercise very easy, please do it. Okay, it's now time for us to give some non-example 7. Okay, let us look at our S3. In that, let's look at our subgroup H, which is generated by this thing, or simply say identity and 1 2, the transposition 1 2. This is the same as subgroup generated by the transposition 1 2. Right? Now I want to know whether H is normal in S3. Okay, let us look at it. Suppose I take 1 2 3. This is an S3, right? Let us look at what is. Therefore, what is 1 2 3? Let us call it sigma. Let us call this alpha. Then I have to say sigma alpha, sigma inverse, whether it belong to H. That's a question, right? What is sigma inverse? Sigma inverse is, see, what I have to do? 3 goes to 1, therefore 1 goes to 3. You have to remember 1 2 3, write it as 2 3 1. And how do I read the sigma inverse? Read from the bottom. 1 goes to 3 and 2 goes to 1 and 3 goes to 2. That is this. This is your sigma inverse. Okay. Therefore, let us look at what is sigma alpha, sigma inverse. Okay. So where does 1 go? 1 goes to 3. Right. And under alpha, 3 goes to 3. Therefore, 1 goes to 3. Then under where does 2 go under sigma inverse? That goes to 1. Under alpha, 1 goes to 2. Under sigma, 2 goes to 3. I am making some mistake. Let me just make sure. Sigma inverse alpha, right? So let us do properly. Under 1, under sigma inverse, it goes to 3. Under alpha, 3 goes to 3, right? And under sigma 3 goes to 1, therefore 1 goes to 1, right? Therefore it must be transpositioned 2 3 3 2. Without writing anything I can say that. Do you follow that? Because let us look at where does 2 go. Under sigma inverse 2 goes to 1. Under alpha where does it go? 1 1 goes to 2. Under sigma where does 2 go to? 3, therefore 2 goes to 3. Is that okay? Therefore this is the transposition 2 3. This is not an element of H, therefore H is not normal in G. So pause, review, proceed. Okay, so we will at least have some example, but in FAB that AX plus B group also one of them will be not normal. I want you to find it out on your own. Now let us prove the much the important characterization of normal subgroup is often used, but I prefer my definition. Okay, let us go to the definition. Okay, so this is an important result. If you want to call it a theorem or a proposition. Let H be a subgroup of G, then the following are equivalent. 1. H is norm in G, that is all X in H, A in G, AX, A inverse belong to H. And 2. For all A in G, the left coset equal to the right coset. Yeah, I'm still sharing the screen. Is this definition clear? Sorry, result. The, the proof is easy because many times textbooks start with this definition, which is normal if left coset is right coset. Okay, but the importance of normal subgroups is because of the first condition. Okay, you see in all the things what we used, that's the first condition. Okay, and because this talks about, remember, this is nothing other than conjugation of x by the group element A, right? This notion of conjugation permeates in various branches of mathematics. It's an important concept. That is why I want to emphasize this definition of normal subgroup. And in fact, you will see almost always we will be using that only in the proofs. Okay, let's go to that. So let us say 1 implies 2, right? Okay, what is that? So I have to prove AX belong to. So I will prove AX is HA and HA is contained in AH, right? These are the two things I have to prove, right? To prove. Okay, let's start. Suppose X belong to AH. Right, that means X is of the form A times H. There exists H in H, so that X equal to AH. Right? Okay. Now what do I know? I know if I multiply, I have to make use of this first property. What is that? AX, A inverse always in H, right? Therefore, let us do. Therefore, if I multiply both sides by H, A inverse, that is X A inverse equal to AH A inverse, but this element is in H because of condition 1. Therefore, it is equal to H1, right? Therefore, X is AH in H1. Sorry, X is X A inverse is H1. That means multiply this, X is H1A. That means H belong to HA. Is it clear? So, this is proved. Okay, the proof of this is something similar. Okay, but just to make sure that I can do it correctly, let me do it. Okay, so let y belong to HA. That means y is of the form sum H times A. right? Therefore, what do you think I will do? I will multiply by A inverse, right? Therefore, A inverse Y is A inverse HA. And remember, if A is an element of G, A inverse also an element of G. Therefore, this is A inverse H, A inverse inverse, right? Therefore, it has to be an element of H. Call this element as H2, right? Therefore, A inverse of Y is H2. So, multiply both sides on the left by A. Therefore, Y equal to AH2. Therefore, Y belong to AH. So, I start with the arbitrary element Y in HA. I proved it's an element of AH. That means HA is a subset of AH. Therefore, HA equal to AH. Prove. So, pause, review, proceed. So, what have we shown? We have shown, therefore, 1 implies 2 is proved. Complete. Now, let us say 2 implies 1. So, what does it mean? You are going to give me an element, let I call H. H in H, A in G. I want to say, prove this. This is all I have to prove. Right? Now, let's look at, I know AH, where does it belong to? It belongs to A times H. But that's equal to HA. Therefore, AH is equal to some H1A. Correct? Because this element is an element of HA. Any element of this is of the form some element of H into A. Right? Now, what do you think I will do? Therefore, multiply on the right by A inverse, then I get H1. Okay. Therefore, AH A inverse is H1. That is an element of H. Therefore, 2 implies 1. Okay. Pause, review, proceed. Okay, so for a subgroup H to be normal, there are two equivalent conditions. One is its left coset by A should be the same as the right coset by A. And the second thing is for every element X in H in H and A in G, AH A inverse must be AH A inverse must be in H. That means H is closed under conjugations, right? Conjugation by every group element you take. For every A, I have a conjugation, right? Do you remember that? X going to AX A inverse is a group homomorphism. Therefore, what it means is under group such a group homomorphisms, it should be H should be mapped to H itself. Am I confusing? Okay, let me just say that. Okay, that is the most important property. Okay, so this is a kind of observation. For every A in G, we define FA to be G to G. Okay, X going to AX A inverse. This we saw is a bijective is an isomorphism of G into G, isomorphism of G onto itself. It has a name, what is called inner automorphisms. Such maps are called inner automorphism. Okay, right. Now suppose H is a subgroup of G, then what happens to FA of H? That is actually H. Right? Actually, by no, I only know it is contained in H because start with an element H in H, then FA of H will be AH A inverse, that is in H. Therefore, I can only show that. But remember, look at FA inverse. Now, this is a subgroup, right? Because under any group homomorphism, the image of a subgroup is a subgroup. Therefore, this is a subgroup. Therefore, I apply F of A inverse. Now, A inverse is an element of G. Therefore, if I apply that F of A inverse of H, that should be contained in F inverse of H. Right? Call this subgroup K. Yeah, FA inverse of K will be contained in FA inverse of K. Of this one. Is that clear? Right. Since K is contained in H, okay, FA inverse, this has This is a set theory. This has to be contained in F inverse of H. Right? But this, you can see this is nothing other than H. Because A inverse, any element here will have the form AH, A inverse, and then A inverse inverse. That is A inverse, A, H, A inverse, A, so I H. Therefore, these are all of H. Therefore, H is contained in F inverse of H for every A in G. Therefore, if I take A inverse, this will be F of A in H. Therefore, H equal to F A of H. You understand this? I proved H is contained in F A inverse of H for all A in G. Therefore, if I take A inverse, that is, therefore it's contained in F A inverse inverse of H. But that is F of A of H. So we have proved H is contained in F A of H and F A of H is contained in H. Therefore, equality. Okay. So the subgroup H is normal if only if under every conjugation map it remains stable. Okay, it's not moved out. If you want to have a look at a picture, that will be nice. Let me have a picture for that. Suppose this is my G, and this is my map F, A. A is where your G. Okay, this is my H. H is normal G. That means, okay, that will go to only H. So this under F A it will go to this only for every A. Is that clear? Okay, right. Now let's go to some again example. Suppose this may be some example 6. Suppose G is abelian. I should have said this much earlier, but I forgot. Okay. Suppose G is abelian, H is any subgroup. Okay. Then H is normal in G. Right? Because if A start with any H, A inverse is same as H inverse. Using associativity, sorry. A inverse. Right? AH is HA. But that is H. In, right? Or more generally, if you look at the thing, AH is same as HA. Because AH is what? A times H as H varies over H. But this is H times A as H varies over H. But each of these elements is equal to each of these elements. Therefore, these sets are equal. Right? So, every subgroup of an abelian group is normal. So, as far as abelian groups are concerned, normal subgroups are not special. Any subgroup is going to be normal. Okay, that's because in the case of abelian groups, conjugation maps, right? Conjugation isomorphisms or inner automorphisms or trivial automorphism, right? AX A inverse will be X, if because A and X commute. We had already seen that, right? So that's the reason why it's not nothing special, right? Now you can ask, if I have a group G in which every subgroup is normal, is G necessarily abelian? Okay, the answer is no. Most often, all algebra people show it as a great piece of price acquisition. Let us do that, because one important group I have not introduced so far, I will introduce it now, and that will be non-abelian group of order 8, and in which every subgroup is normal. Okay, that is called quaternion groups. We will go to that. Okay, so converse is not true. What does that mean? There exists a non-abelian group non-commutative group. G said that every subgroup is normal. Okay, that is the so-called quaternion group. Quaternion group of 8 elements. This is 8 elements. Okay, we will do that. So I'll give the group in a very concrete manner. Okay, that also will be somewhat interesting. The way I do that, you may like it possibly, right? And then I'll give an abstract way. Do you remember when we did a dihedral group of order T4? We said it's enough if I know R and S. R is the rotation, okay, by pi by 4, and S is a reflection along the either the vertices or along the midpoints of the opposite sides. If you have not seen it, forget it. Okay, if you have not watched my dihedral group, you can forget it. But I'm going to do it now in its different setup. So the groups are, see, they are going to be 2 by 2 matrices with complex entries. And the entries are going to be plus or minus 1 and plus or minus identity, nothing more. Okay. Now, the way I want to do is I want to fill it in such a way, okay, either it has only the plus or the in this, the entries should be only in this or only in this. And the entries are going to be only either diagonal entries or anti-diagonal. What do I mean by anti-diagonal? Either this or this entry. The rest are all 0. If I filled it, this should be 0. Or if I filled this, these two should be 0. Right? And the third condition is my determinant should always be 1. Okay? Instead of trying to write from memory, I want to use this. Okay? With these rules, I want to fill 8 matrices. Let us see whether I succeed. Okay? Please help me if I do some mistake. So, this identity element naturally is 1, 0, 1. Matrix multiplication. See? Right? Then for I want to determine minus 1 also you can have. Right? Yes? So it's called minus 1. Right? Now I want with I. Okay? Let me call this I, usually denotes by bold I. This I want I, therefore I can do it I. And once I put this I, this has to be 0. This has to be I or minus I. But then remember the determinant has to be I into I will be my I squared, which will be minus 1, therefore it must be minus I. Therefore minus I also is there. Right? Maybe I will, yeah, okay, this will be minus I 0, 0, I. Right? Okay. Next is I have done everything to diagonal things. Therefore 1, 2, 3, 4 elements. Now we have to do anti-diagonal. So if anti-diagonal, what do I do? If I put 1 here, determinant has to be 1, therefore it has to be minus 1. Right? Yeah? Is that clear? And since it's there, it's here. Negative will also should be there. Minus 1, 1, 0. This will also be there. And here, with respect to I, what do I have to do? I have to put another one. Here it will be 0. I have an I, and this has to be 0. Therefore, it has to be I, because it will be minus I squared, which will be 1. Therefore, again, 0, minus I, 0. These are the 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 elements. And binary operation is a matrix multiplication. Right? Now, let us look at this element. Yeah. Yeah, let us look at this I and call this as J. Okay. Now let us look at what is Ij. This is a bold space. Okay. I do not know how to write it, so I'm just writing it. Okay. You know the like the vector notation, right? Think of it that way, right? Therefore, it's going to be I is going to be I 0 0 minus I J. I just want to make sure only one. After that, I'm going to leave it to you. I'm not going to do that. I 0. What is the product? This into this is 0 and this is minus 1 into 0, right? This times this and this time this is just to make sure I'm doing this minus I, right? Plus this minus I squared, therefore it's plus 1 and 0. So I'm going to get this element. So call this as K. Call this as element as K, right? So what I want you to observe, okay, this exercise, I'm not going to do it. It will be quite boring for me. So I squared, this is I squared is minus 1 is J squared is minus 1 is K squared is minus 1. K is this. And take any two product I and J, it will be the third one. And Ij product will be minus Ji. And if I take in that order Ij and Jk will be I and Ki will be J. The order is important here. If you change the order, they are all different. That is Ik is minus of Ki and Jk is minus of Kj. Please verify. Okay. Then this becomes a group. I do not know what is the notation. Maybe I'll write Y8 for maybe Q8. Yeah, quaternion, right? Yeah. So let us write Q8. Okay. Quaternion. This is, we do not make quaternion group. We can check all these things. Right. Now, what are if suppose H is a subgroup of Q8, not this ordinary Q8, okay, not rational numbers. So what are the orders, possible orders? H has to be 1 or 8. In this case is a trivial identity. In this case is a full Q8, right? Otherwise 2 and 4. Suppose H is of order 4, then in the index of G, H is 2. Therefore H is normal, right? Therefore, now I will have to look at group of elements of order 4. Now, if H is of order, then it has to be one of these elements. Identity I, right? And or some such thing. H equal to, let us say, plus or minus, sorry, I am very sorry. If H is of order 2, then it has to be only plus or minus identity, because you can see I to the power 4, J to the power 4 and K to the power 4 will be identity. Therefore, they are all elements of order 4. Okay, order of these elements will be 4. Therefore, if it's a subgroup of order 2, then there are only two elements which will have that property, namely plus or minus 1, not identity, plus or minus 1. This is a subgroup. Okay, but this H is normal in G. Why? Because if I take any element, if identity no problem, if I take minus 1 times I inverse, okay, that will be, you can see it's going to be, since this is in the center, okay, remember 1 times any group element X in G is X, and similarly minus 1 will also be the same. Minus 1 times X is also equal to X. Okay, therefore X times minus 1. I think I'm losing my focus. I'm sorry. Okay, 1x 1 inverse is 1x1, which is x, and minus 1x minus 1 will be x. Minus 1 inverse is minus 1, right? Minus 1 inverse minus 1. Okay, therefore minus 1 x minus 1, if you multiply, you will find it is x. Right. Remember what I am doing is minus 1 0 0 minus 1, and x is something into minus 1 0 0. Right? This is just a minus sign comes out, it's just minus 1. Okay, this also minus 1 comes out because scalars. After this, the identity, therefore it is x. Is that clear? So that gives a very general result. Let us call, okay, if H is a subgroup of the center of G, and we know center of G is normal in G. Why? Because you start with any Z in center of G and A in G, then AZ A inverse will be, because Z is in the center, it is same as Z A Z inverse, which is Z, right? Therefore this is in Z, namely Z, and hence. So this is correct. Now I claim H is also normal in G for the same reason. Normal in G, because you start with any H, then what happens? Start with any A here, AH A inverse, but H is in G, but H is the center, right? Therefore it is same as HA inverse, therefore H. Therefore H is any subgroup of this implies H is normal in G. In particular, center is normal in G. Now therefore, now go back, okay, the only subgroup of order 2 is actually plus or minus 1, okay, and it is in the center. It is the center of the quaternion group. Okay, please check all those things. The center of quaternion 8 is plus or minus 1, and hence it's normal. And the only subgroup of order 2 in Q8, if it's a subgroup order 2, it must have two elements, right? E and A, right? That means A squared must be equal to identity. The only element which satisfy that property are plus or minus 1. Therefore, the only subgroup of order 2 is 2. This is plus or minus 1. But that is equal to the center of Q8. Right? Okay. Is there anything else which I have to do? So, I hope I have done whatever I wanted to say about normal subgroups. In case I had forgotten, because I don't come prepared, I don't know the list of things which I have to do. Whatever comes to my mind, I keep doing. So sometime I miss the point, I have to come back and cover it. If you are following my videos, you must have got used to this. Okay? Bad habit of mine, right? Okay. Anyway, so please go through that. And that ends. The only thing, the key takeaway, even those who had already learned group theory a lot, never remember a normal subgroup as left coset equal to right coset. The best way to remember is conjugation. Okay, for every H in H, for every element A in G, AH A inverse belong to H. Okay, that is H is closed under conjugation maps. Whatever be the conjugation, that is the most important characterization. In fact, that is the correct definition, in my opinion, of a normal group. If you carry that away, I'll be happy. Okay, we will meet again. Thank you very much.